Okay, here's another example, or an example for class 13 and ME370. So we have this flat plate. It's made of brittle material, and it's 75 millimeters wide, 5 millimeters thick, and has two notches, each of which are 5 millimeters radius at the bottom, right here, right? And if the bar is loaded axially with 10 kilonewtons, right, so coming out that way right there with 10 kilonewtons, we want, and the tensile strength is 200 megapascals. What is the safety factor against tensile failure? Let me take a little pause here. Okay, and so summarizing what we have here is, and what we want to do is try to match what's in the book. All right, so this is in the back, tables, you see there's a number of them. Table A15, let me move this upwards so you can see it better. All right, so we have different A15-1, A15-2, A15-3. This is our scenario right here. So we want to try, one of our first tasks is to look at this situation and compare it to our situation and figure out what parameters we're going to want. So we can see that D is defined as that distance in between the bottom of the notches. Here's R, here's W. For the F over A that we're used for the nominal stress, that's just going to be D times the thickness, right? The thickness out of the page. And we're going to need R over D. All right, and you decided just to jump right in there, didn't you? And we're going to need W over D, right? So these are the parameters. So we need to take our situation and match them to this. Maximize our space here, try to straighten that out. So we see that D is 50 millimeters right here, right? W is 75 millimeters. R is 5 millimeters. And T is also 5 millimeters. And the force on the thing is the 10 kilonewtons, right? So we'll take the W over D first, is 75 over 50. So we get 1.5, and then we have the R over D is going to be 5 over 50, or 0.1. So what we do here, as best we can, is we take a look at our 1.5. We are lucky enough, well, were we lucky? I actually picked it. 1.5 right here is the line to pick, right? That's the W over D, so we're using 1.5. And then we have the R over D we found to be as 0.1. So where they intersect, you'll note that there's 2.2 and 2.4. Halfway in between would be 2.4 into the thing. Am I doing this wrong? Yes, I am. Okay. See, I made a classic mistake. I was using this curve where I should use this curve right there, right? Because notice 1.5 is below this, so this curve is 1.05. This curve is 1.1. This curve is 1.2. So this is the curve that's 1.5. And you look, and it intersects at 0.1 at exactly 2.6, or nearly exactly 2.6. Close enough for us. So our KT is 2.6. I seem to recall making this mistake several times in classes. You'd think I would learn, but so KT is approximately 2.6. That approximate is just to acknowledge that we took it from a table. So the area, we were told, is DT, right, at 50 times 5, right? So that's, you can think of that as being the cross-sectional area that's right in that section right there, right? So that's the evenly distributed one would be predicting that it would go across that area. So 0.05 times 0.005, 2.5 e minus 4, those are meters squared. If we wanted the nominal stress is just F over A, so 10,000 newtons divided by 2.5 e minus 4, and we're left with 40 million, or as we know it, 40 megapascals. And so the maximum is going to be predicted to be KT times the nominal, or 2.6 times 40, and we get 104 megapascals. And then we get a safety factor of ultimate divided by stress max, and that should be 200 divided by 104, which is going to be 1.92. Now I got the SolidWorks running right here. Let's see how long the video is. Only 6-minute video. So let's go ahead and make this thing in SolidWorks. Why did I say? So I'm going to create a new part. Oh, yeah. So I'm good. Yeah, it's still doing it because it's the screen thing. Okay. So I'm going to make a new part. I'm going to make it in millimeters. It's just easier to input as meters, as millimeters. So I'm going to change the thing to millimeters, and I'm going to use the front. It's just nice to have in the XY plane. I'll create a sketch. Didn't say how long the thing was. No, it did actually. It did actually say it. So let me just put it in here. It said it was 150 millimeters long, and it's 75 wide. Okay, and then instead of trying to make the notches in here, it's just easier to make it later on. So I'm going to extrude that 5 millimeters, so it's very thin, quite thin. And now I'm going to sketch onto this, and it's going to be easiest, I think, for here. See, am I in a sketch? Not in a sketch. In a sketch now. Okay, so I'm in a sketch. I'm gonna bring this down to right here, and I'm going to create a circle that's going to be on here, but it ends onto that point. Okay, and I'm doing that for a reason, because now you know, it was 50 from here, but now I can make a dimension that's right to there. And this guy was 5 millimeters radius, so he's a 10 millimeter diameter. And now I want to come up to the side right there, so it's there, and then it's probably easier to do it to go escape and go to this right to there, and then I'm in here. Okay, now I need to trim this off, and now you see that the thing is full, and we will now, let's see, we get out of this, let's cut it, extrude cut. I like to go through all when I do that, just make sure it's not the right depth. Okay, so let's take this feature and let's mirror it. I believe we can mirror it. Pattern, yes, mirror. So it's going to mirror that feature, and we're going to do it about the top plane, and it looks like it's going to be correct. And that's it right there, right? And you can measure that distance. So that is the means of doing this. And by the way, I've set this up on this cut right here. So like I could potentially fix this up. Now, something I will warn you of if you try to do this with do a whole bunch of different ones for different sizes of the things. Sometimes you don't need these lines right here. Sometimes like the radius is so large that it actually comes up above. So you might have to change the sketch in order to be able to do that. Just warning you. So we'll make a simulation on this and create a new study. We're going to pick a static, is fine. And material, the materials don't matter nearly as much because for deflection they matter, but here they're not going to matter a whole lot. And the strength doesn't matter. The strength actually will only show up as sort of like a line on the yield strength. Sometimes will show up as like a little pointer on the scale, but it doesn't change what the nominal strength of the thing's going to be. But you can take a look at the yield strength of this is 620 in that alloy, and if you wanted to come down, and of course they changed things on me. What is that going? Oh yeah, okay. So that's megapascals. You see the yield strength is 351. If you go to A36, where's A36? Is right here. You can see that this one has a yield strength of 250, right? So we're actually something smaller than that. Maybe someone's kind of a low carbon with no, yeah, they go 180 right there of a hot rolled and cold drawn. You can see that that's 1015. 1020, that's 350. Yeah. Iron super alloy, that's a weird thing. Anyway, it doesn't really matter what we apply on here. So I'm just going to go back to that. It'll change the deflection once again. So I did click on that, right? Apply. Yeah, we can close it. And you can see that the material is right here. So we put the fix, right click on there. Put a fix right onto the end. And then we put external load. And this external load will be pretty easy to do because it's going to be perpendicular. We need to go reverse the direction. And remember that it's 10,000 newtons. And we can go ahead and just mesh and run this. Let's first create a mesh. Let's see what that mesh looks like. It's kind of a very coarse mesh right here. So we will, let's run it though. Let's run it with this. Right click on that top one, static. You can see that very quick. Let's edit the definition because I would like to see megapascals. And let's change the scaling on here. I'm anticipating somewhere in the 100, right near 100. So let's make, well, first off, this is going to be 0. Oh, I also should change something. I forgot. Let me change this instead of von Mises. Let's just make it normal stress in the X direction. That's important, right? Because you'll see what von Mises is pretty soon. And here we will make this, I'm just going to make it 100. There you go. And then for my scale down below, let's see, I want to make, it'll be floating, and I want, let me go one decimal place. I'll go 1 decimal place. I don't like to see too many decimal places. And 10, that's a good distribution. Let me see the discrete. And I might actually show the mesh. Oh, and let's just, for the sake of argument here, let's put on the maximum. And you can see that I have 116 versus my prediction off of Peterson of being 104. But this is a crude mesh. It's also, we have to be, look, you can only see that there's only like one node through the thickness of this thing. So that becomes kind of an issue mathematically in the way that this is created. So let's, something I was thinking of doing as part of this that you should know of the existence of. So right from here, what I can do back in the modeling of the thing is I can insert a curve. This is called a split line. Insert curve split line. And what that does is it's going to split this face. That was my goal. First off, let me see. This is direction of pull. No, I don't want to sell it on intersection. And this is going to be splitting bodies. So the splitting body I'm going to use is the right plane, and then I'm going to click right in here and right in here. And okay. Now, I should have put a line in there. I don't see the line. Let me see the line again. Okay. So I don't know why it's not. Oh, you know why? I know what I'm doing. I know what's wrong going on. I think I changed my settings. So you really would want to see this. So let me see if hide show. It's tangencies that you're not seeing. So yeah, tangents removed. So tangent edges visible. There you go. So now you can see that's the split line. That's what I added right into there. I turned those off for graphic communications class. But right there, that's where the split line is. And what that does is it forces some nodes to be onto that position. They already were going to be in this case, but now there's definitely always going to be nodes onto that line because it's defined. And then I run the thing. Not going to change the solution any. It did, interestingly, it made the max on top of there. They should be symmetrical though, so it's just a numerical thing. Oh, and by the way, if you want to be entertained, you can always animate this, right? We blue, 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 blue. You can slow it down. Blue. All right. Enough of that. So what it allows us to do, the reason why we want to do it, is we might want to now take a look at the stresses along that line instead. And you can see that they actually have several nodes right in there, but you could see that there's some variation, right? There's a 103 is in there. So the average is actually 108.7, even though that one node is 116. And that's an indicator that you need more elements. If they can vary that much in a small location, you really need more elements. And we could just go to this and create the mesh and move this slider over. And we might even do that. Let's just see what the effect is on here. And you can see there's way more elements, and you can run the thing, and it might take a little longer, but not much to run. But you can see that the stress went up here to 118, so that's moving away from what we wanted. List selected here. Let's take a look at what those are. You can see that there's more nodes going through the center of the thing, and you can see that the average went to 112. And okay, so now that was like a global addition. I don't know why we needed dimension. I don't even know where that came from. Now underneath the mesh, we could right click and apply mesh controls. This is SolidWorks method of trying to control what the mesh is locally. I'm just going to put it in this one spot, and I'm going to ramp this thing up as much as it can go. These are like the minimum size of an element, and here is like the pace at which they disperse away from that location. So we put those on here, and we create the mesh now. And by the way, sometimes this doesn't work very well. It's not a very good mesh generating tool. So it didn't work there, and I don't know why. I always get frustrated by this thing. I'm going to edit this definition here, and I'm going to make this thing smaller. And now let me try this mesh. Create mesh. You You better work this time. Okay, look and you can see how much tighter it is in that location. So let me see if I can run this and what happens. It's much more efficient to make localized stress elements along those lines. But there still can be some effect, so we might want to explore how much further out we might go. So what is the maximum here? Now the maximum is 118. I still get 118. But I can also see, and we would expect it to be pretty homogeneous across the length. There's no real reason that it wouldn't, except for some serious deflection taking place. But you could see now we get the average of 117 to the thing. You can also hit this little guy, this little plot little guy, and it'll kind of show you what the distribution is. This parametric distance isn't, it just means across the length, that there's no real numeric there. But you could kind of see that it's largest in the center and it gets smaller towards the outside. So you can see that the thickness does matter on this thing. And that's about it. I think there's a lot of information right in there. But what you really want to do is, if you can, edit this definition of this control, and I think going down or maybe going up. Let's try it with up. I think that will make the number of elements. And by the way, sometimes that makes the thing so it won't mesh. Warning you. Yeah, so that went the wrong direction here. I always forget. So I think I got to go down. Which doesn't make sense. You can only go to 1.1, I believe. It always frustrates me that you can't get smaller. You can't do more mesh controls than this. Still didn't do great right there. So what I will do as part of this maybe is edit definition. I might actually grab a hold of these lines like this right here. By the way, you should really do it on both, but it doesn't. Truth be told, you don't have to model something that's symmetric. You don't have to model both sides of the thing. That's another way to really reduce the amount of nodes. You can cut them in half by, you give a boundary condition that tells the thing that it's symmetrical about a particular boundary. That's a very common thing to do. Right? And whoop, see, there you go. There's some serious meshing going on right there, right? And so let's see what happens. That's one of the fun things about the FEA, especially when you make small models that you can solve quickly, as opposed to the ones that would take days at Electric Boat to solve at faraway computers. But now you can start to see the thing take some time. You go to the convergence thing, you can see the convergence plot. And it's not giving me the live plot for some reason. There you go. It'll give me the results. Boom. But it didn't improve it a whole lot, right? It's not that much. All that effort, more computer power. Got to start to push the computer what it can do, and it looks to me like we pretty much narrowed down to this seems to be what the theoretical thing is. And look how smooth much smoother what that piece was. Let's go back and you could even take a. You could just suppress this, right? So suppress mesh controls. No, should be a suppress. Yeah, suppress. So create mesh. And then run it. can see our result actually wasn't all that bad compared to what we had. It'd be interesting to see the results of this done in ANSYS and what they would predict to compare them. But you could see here's across the thickness right there along those lines, and you can see how jagged the thing is. So that's a pretty nifty. It's a good idea to turn this mesh off when you're done. When this isn't the thing that you want to see, because the mesh can get in the way of, especially if you're if you were to have to print the thing out to show somebody. But when you're trying to investigate the mesh, there's good information to know when you're putting the thing together. You can see how it varies across different nodes. So there you go. More information than you wanted, but could be useful to someone.